Welcome to AI Paper Podcasts. Today, we're looking at the preprint Imagination Helps Visual Reasoning, but not yet in latent space, from researchers at Tsinghua University and Beijing Jiao Tom University.
Yeah, this is a fascinating one.
It really is. And let's just fire off the TLDR right away for the AI researchers and ML engineers listening. So, multimodal large language models have been trying to imagine visual concepts using hidden states.
Right, which is known as Latent Visual Reasoning, or LVR.
Exactly. Instead of relying on external tools, they use these hidden states. It sounds incredibly advanced, like giving the AI a true mind's eye. But this paper proves that current latent tokens are actually a mirage.
A complete illusion. By using Causal Mediation Analysis, the researchers discovered that these latent tokens basically collapse into identical states regardless of the input.
Yeah.
And even wilder, if you intercept the model's forward pass and replace its latent thoughts with pure Gaussian noise, the final answer barely changes.
Which is just crazy. But to fix this, the authors created CapImagine. It's a straightforward method that forces the model to explicitly imagine visual changes in text space using a specific think-image tag.
And it works. It beats complex latent baselines like Monet and LVR by significant margins across high-resolution benchmarks.
Not to mention it runs twice as fast as tool-augmented models.
Which is huge for deployment.
Right. So let's step back and look at the promise versus the reality here. Imagine you are building an agentic MLLM right now. Traditionally, if you want it to perceive fine-grained details, you use rigid tools.
Like a zoom-in function or drawing bounding boxes.
Exactly. You give it APIs, it gets the job done, but it's highly mechanical.
And that mechanical bottleneck is exactly why latent visual reasoning sounded so appealing in theory. You look at models like Mirage and Monet, and the goal is to bypass rigid tools entirely.
Because the visual and text embeddings are already aligned in the model.
Right, so why not just train the MLLM to output latent tokens that are compatible with those visual embeddings?
Yeah.
The hope was to unlock a broader, unconstrained visual imagination.
In theory, you just let the transformer dream up whatever visual transformations it needs. And empirically, these models were posting great benchmark scores.
They were. But the authors of this paper were skeptical. They wanted to know if the model was actually using that latent space to reason, or if it was just, faking it.
Faking it to satisfy the objective function.
Exactly. So they use Causal Mediation Analysis.
Which is a really rigorous framework.
Highly rigorous. You treat the input sequence, so the images in the user's question, as the treatment, which we call X.
Okay.
Then the intermediate latent tokens are the mediator, Z, and the final generated answer is the outcome, Y.
So X points to Z and Z points to Y.
Precisely. And for this to be genuine reasoning, changing the input X has to change the latent state Z. And that latent state Z has to directly influence the outcome Y.
But the architecture failed at the very first step. Finding one from the paper is this massive input latent disconnect. When they altered the input images and questions, doing instance-level perturbations, the latent tokens barely changed.
The geometric reality is kind of shocking. They measured the cosine similarity of these tokens. If you sample tokens at the same autoregressive position across entirely different instances,
different images, different questions,
completely disparate tasks, the tokens are highly identical. They encode virtually zero specific information about the input X.
It's optimization laziness, really. The surrounding text context has enough statistical clues, so the network just takes the path of least resistance. It doesn't bother constructing a complex visual representation.
And it gets worse the longer it thinks. The progressive collapse is undeniable.
Oh, right, the intra-instance analysis.
Yeah. With every autoregressive step, the LLM backbone makes smaller and smaller modifications to the hidden states. The tokens just rapidly collapse into a tight uniform cluster. For standard LVR, this token collapse happens by the second reasoning step. By step 2, it has abandoned any distinct visual processing. For Monet, it happens by the 5th step.
And what's wild is that normal text and image tokens in those exact same models show totally healthy, distinct semantics.
Very low cosine similarity. The degradation is completely confined to the latent visual reasoning pathway.
So that brings us to the Z to Y disconnect. What happens if you intentionally break the latent tokens during inference?
This is my favorite part of the paper. The ablation studies are brutal. They tested extreme interventions on Monet and Mirage, injecting Gaussian noise.
Just injecting static.
Right. Or replacing the tokens entirely with Gaussian noise, setting them to near zero. Or, for Monet, forcing all latent tokens across all positions to be a single identical tensor.
So you're basically lobotomizing the model's visual mind's eye, and the shocking part, it didn't matter.
It completely ignored it.
On the V-star benchmark, which demands intense visual imagination to find hidden details, applying a shared identical tensor to Monet actually improved performance by 0.5%.
It went up.
It went up. And on HRBench 4K and MME Real-World Light, performance only dropped by an irrelevant 1.0 and 0.7%.
So for the Emerald pipelines you're building right now, the takeaway is clear. Current models are finding implicit shortcuts.
They're bypassing the visual reasoning entirely.
Completely. The latent tokens are basically acting like Zoc prompts, or rhythmic placeholders. They just give the text backbone a few extra compute steps to process the surrounding text. They aren't carrying visual thought.
They proved that beautifully with the probing analysis, the CART example.
Oh, the derived questions test, yes. The logic is simple. If a latent token holds visual semantics, it should be able to answer follow-up questions about that exact same image.
So the original prompt is, what is the color of the cart? The model generates its latent reasoning tokens and an answer. Then you freeze those exact latent tokens.
You take the original image away completely.
Right, no image in the context window. And you prompt it with a derived question based just on those latent tokens. How many wheels does the cart have?
And remember, it's the exact same object. If it built a geometric representation to find the color, the wheels should be in there.
But when prompted with just the latent tokens, Monet scored 33.33%, which is significantly worse than a blind guess on that data set, which sits at 43.33%.
The visual semantics simply aren't there. It's worse than random chance.
Okay, so if the continuous latent space is a dead end for now, how do we actually achieve visual imagination? We still need to solve the engineering problem without falling back on rigid APIs.
And that is where the authors pivot to CapImagine. Instead of relying on hidden states, CapImagine explicitly verbalizes the visual transitions in discrete text.
Using that think-image tag.
Exactly. It forces the model to expose its reasoning chain.
So instead of black box tokens, it outputs highly descriptive text. Like if it's looking at a chart, it'll explicitly say, suppose a red rectangle had been marked on the lower part of the image, highlighting Chile and Greenland.
Right. The language itself is doing the heavy lifting of the visual semantics. But for the ML engineers listening, the dataset construction here is a masterclass.
Crucial stuff.
They didn't just scrape new data. To get a strict apples-to-apples comparison, they took the existing Monet SFT 125K dataset, which the latent models were trained on, and rewrote it using Qwen 3VL4B.
Generating text descriptions for every visual manipulation, like zooming or drawing lines.
Yes, but here is the massive pitfall they uncovered. And you really need to note this for your own training data. They found that 94.88% of the Monet dataset consisted of visual coty data that was deeply flawed.
Almost 95%. Flawed how?
In ways that actively destroy causal learning. First, rampant misalignment. The intermediate observation might say a graph peaks in 2020, but the hard-coded ground truth answer says 2019.
Oh man, the reasoning explicitly contradicts the output.
Exactly. And second, ambiguous questions. A prompt asks, what is the color of the car? But there are 5 different cars in the image and no bounding box.
So if you train on that, the model learns that its intermediate reasoning steps are totally irrelevant.
It learns to ignore its own thoughts. To fix this, they built a really aggressive, automated LLM filtering pipeline.
They evaluated semantic consistency between the generated visual observation and the final answer.
Any illogical contradiction, they dropped it. Unanswerable prompt, dropped it. They whittled 125,000 noisy instances down to just 17,000 high-quality, pristine examples.
And they proved the value of that filtering. In an ablation study, if you skip the filtering, the model's performance continuously declines during training.
Without clean causal links, the model just optimizes for hallucination.
So they trained CapImagine on these 17,000 pristine examples, building on Qwen 2.5 VL7B, and the performance gains are massive.
It consistently outperforms the complex latent baseline Monet,
beating it by 4.0% on HRBench 8K, 2.6% on V-star, and an impressive 4.9% on MME Real-World Light.
And it crushes the latent models on abstract visual reasoning. Look at the B-Link benchmark, which tests multi-view reasoning and jigsaw puzzle solving. CapImagine wins by over 10 points and scores 6.1% higher on Table VQA.
Verbalizing structural logic anchors the reasoning process in a way homogeneous latent tokens just can't do. But, and this is key, They had to prove CapImagine wasn't just finding a new shortcut.
Right, the dependency analysis. They needed to prove causality. So they repeated the causal mediation analysis, but this time with the explicit text tokens as the mediator Z.
And the results flipped. When they altered the input X, the intermediate text tokens were highly distinct. Very low cosine similarity.
But the real proof was the intervention. They let CapImagine generate its think-image text sequence. Then they paused the forward pass and used Qwen 332b to deliberately, maliciously edit that text sequence.
They poisoned the text, so the reasoning led to a false conclusion.
And they fed it back in. Unlike the latent models that completely ignore Gaussian noise, CapImagine's performance sharply dropped. It fell below random guess levels.
Proving a true causal link? If you manipulate the textual imagination, you successfully manipulate the final answer. The model is actually relying on it.
It is causally effective, it's interpretable, and from a deployment angle, the efficiency is fantastic.
Yeah, let's talk hardware. Even though it's outputting 50 to 100 explicit text tokens instead of a few dense vectors, CapImagine is just as fast as Monet during inference.
Autoregressive text generation is highly optimized today. Plus, it completely bypasses the computationally heavy latent projection layers.
And it's almost twice as fast as tool-using models like DeepEyes because there's no network latency from API calls.
Exactly.
So the core value for you listening today is clear. If you are building reasoning models, explicit text-based reasoning, actually outlining visual thoughts in language, is far more causally effective, interpretable, and performant than forcing reasoning into black box latent tokens. Imagination helps visual reasoning, but as the title says, not yet in latent space.
Not yet. But I want to leave everyone with a final provocative thought from the paper's limitations section. Natural language is highly effective right now, but it is inherently limited in granularity.
It's discrete.
Yes, discrete vocabulary cannot match the massive theoretical information capacity of a high-dimensional, continuous latent space.
So the failure of current latent tokens isn't necessarily a failure of the concept itself. It's a failure of our current training paradigms to enforce causality. If an LLM is only penalized on the final answer, it will always find the laziest path.
Always.
So for the researchers listening right now, how do we construct a loss function that forces high-dimensional latent space to actually hold causal reasoning chains? Maybe using contrastive predictive coding or energy-based constraints on intermediate steps. Whoever solves that might unlock the true next generation of multimodal AI.
That is the million-dollar puzzle.
It really is. Until then, keep your reasoning explicit, filter your datasets rigorously, and we'll see you on the next deep dive.